internal force convection. So first of all, we discuss the concept of mean temperature, uh, and then we discuss about the concept of mean temperature and mean velocity. So mean temperature is a uniform value of temperature which would produce the same energy flow rate at a cross section, which actual velocity profile, which is shown by inverse parabola here. So that would produce. So it, and the relation here is involving the temperature distribution as well as velocity distribution. So it means that first of all we need to calculate velocity distribution by the solution of boundary layer equation, and then we can determine the mean temperature value. So that is something which we are going to discuss today. So then we discussed about that. You also know from your fluid mechanics knowledge that the Reynolds number in case of pipe flow, if the flow is laminar, then the value of Reynolds number should be less than 2300, and then above that, that whether that is either it is transitional flow, which is between 2300 and 10,000, and then above 10,000 it is fully developed turbulent flow, right? And then if we have got non-circular pipes, then we need to use hydraulic diameter to calculate the effective diameter for the calculation of Reynolds number. Okay, and then we discussed about the entrance region. In case of velocity boundary layer, we call it hydrodynamic entrance region, and then fully developed region. So it means that the velocity along a streamline does not change in the fully developed flow, which is after some distances. And then we also discussed about thermally fully developed region. So in that, this ratio is independent of x, which is Ts minus T divided by Ts minus Tm. And then in the last section of the class, we discussed that in the entrance region, H value is more because the velocity gradient at the pipe surface is more in the entrance region, and then similarly the Nusselt number or Hx value is also more because the temperature gradient at R is equal to R, which is shown here at R is equal to R, that is more in the entrance region. So that's why they are more at the start of the pipe, and then once the fully developed flow is achieved, then the value of H and friction factor becomes constant. So that is something which is also clear from this diagram. Now, what is this value of the entrance region? Because if we see here, let me take you on the whiteboard. If we have got a pipe flow, so if this is pipe, so first here it would be entrance region. So for the velocity boundary layer, we call it LH, hydrodynamic entrance length. So LH value would be equal to for the laminar flow, LH would be equal to 0.005 Reynolds number into diameter. What is diameter here? Diameter is this diameter of the pipe. So it means that if we know the Reynolds number of the flow and diameter of the flow, then we can estimate the length after which the flow would become turbulent, or not turbulent but fully developed. Fully developed, right? So how do we know that it is fully developed? Because then the velocity profile would be something like parabolic, and the value of and the velocity along a streamline would remain constant, right? So uh, and then LH, we call it LH, laminar And then if we want to know LT laminar, which mean LT laminar, LT laminar means that we are the uh, temperature thermal boundary layer. So T means thermal. So for this, it is just this value, or I should write it LH laminar into Prandtl number. So we can write it like this: 0.05 Prandtl number into diameter. So for the laminar flow, we can calculate the thermal entrance region by 0.0 by this formula. Now coming towards turbulent flow, what if the flow in the pipe is turbulent? It means the Reynolds number is greater than 10,000. So in that case, there is a rough estimation which we usually use. So let me draw it again. So in this case, we say that if we are talking about LH turbulent, then we say that LH turbulent would be equal to, and it is also equal to LT turbulent, which is thermal boundary layer, and that is equal to simply 10D. So it means that if the flow through the pipe is turbulent, then we say that it takes like 10 diameters in order to flow to become fully developed for the turbulent flows. So 10D distance would be the entrance length for velocity boundary layer as well as for the thermal boundary layer. So I hope that this point is clear. So that is an approximation because so we can say that uh, we can put like this. This is kind of approximation. So we say it that this is the case. So if I show you the diagram for the Nusselt number, just a minute. Here in the diagram, let me make it and a little bit more zoomed in view. Now you can see that we have got Nusselt number for two boundary conditions. Yes, anything? Okay, Usman Vakil has just joined. So as we were discussing here, that if you look if you concentrate at the solid lines at the moment, and you can see that it has been different curves has been drawn for the Nusselt number and zero mean entrance of the length, and here we have got on the x-axis x upon d. X upon d mean the ratio of distance from the leading edge of the pipe and then divided by its diameter. So at the start of the pipe, you can easily see that for all the cases, the Nusselt number is very high value, and then it keeps on decreasing, and then after some distance, the this curve becomes independent of x. It means that Nusselt number is a constant value. So first of all, if you look at the bottom curve, so it is at 10,000. So if you see here that for the 10,000 case, that after at x upon d 2 it becomes kind of constant. So it means that the entrance region for this curve is like 2 into diameter. But if you look at the top curve here, which is 2 lakh curve, so for this case, if you look here that the Reynolds number is 2 lakh, so in this case you can easily see that for the turbulent flow that x upon d is kind of 10 value, after which it becomes kind of straight line. So it means that that assumption of 10D is safe for us to have this. So it means that after 10 into diameter length, the flow inside the pipe would be, it would be safe to assume that the flow inside the pipe is turbulent. So it means that if we go back here, diameter of this pipe is maybe 2 centimeters. So it means that I have to wear like 20 centimeter in the x direction before I can assume that the flow through the pipe is turbulent. So that is something that is a rough estimate, but of course we can calculate the exact value of entrance length by the relations. But that is the rough estimate of 10 diameter that we use as initial entrance length. Okay, so that was the discussion of entrance length. Now, in order to, if now let me pen this a little bit. Now we would be going to talk about general thermal analysis of flow through pipes. Pipes, or we can say ducts, whatever we call it, pipes and ducts. So in this case, usually if we want to do analysis, if I draw it here, we have kind of a situation that uh, if here we take an element, kind of not differential element, but we take a piece of pipe. So what will happen that the flow would come in with some energy which is coming in, E dot in, and some of the heat would be coming in or out depending upon the surface temperature. If the surface temperature is more than the fluid temperature, so then the energy would be coming in. So that would be the case of heating of fluid uh, from the outside energy. So it can be solar energy as well. So which is the case in the summers, and then something is going out here, right? So if we apply the energy so if we say that this is entrance, so at this point the temperature was, mean temperature was Ti. At this, the mean temperature was T out. So if I want to write E dot in terms of Ti, is there any formula I can use? E dot in किसके इक्वल होता है जी?
Sir, Q naught delta T.
नहीं, if I know the mass flow rate here for the fluid which is
Sir,
flowing through
MC
this
delta T.
pipe, m dot Cp Ti, okay, and then E dot out would be equal to m dot Cp T E, if the temperature here is Te, okay, not Tm. So the heat which is coming here, that is by convection, okay. So that would be equal to what would be the value. So if I say that the heat which is coming here, okay, before we go further, there are two types of boundary conditions which we usually use for the internal flow. One is constant heat flux boundary condition, right? So this boundary condition is realized, or we can see this boundary condition being applicable when we have got constant heat flux coming in from the pipe surface or going out. So that would be the case when the solar heat is coming in, or the pipe is being subjected to electrical resistance heating. So it would give us some heat coming into this pipe. So that is one case, one of the boundary condition, and then the second boundary condition is constant temperature boundary condition. So that boundary condition is we can see that boundary condition when we have got phase change process at the pipe surface. So it means that either there is evaporation of some vapor or condensation of air at the surface. So then we would have constant temperature boundary condition. So now we are going to discuss the effect of these two boundary conditions on the pipe flow uh, one by one. So first of all, we consider the constant heat flux boundary condition. So for the constant heat flux boundary condition, if we assume that this Q which is coming in, so because the heat flux is constant, so we can say heat flux value at the surface is Qs. So the total heat which is coming in, then that would be equal to Qs into surface area, which is As for this length of the pipe. So that length of the pipe would be this length into pi d. Pi d is the diameter of the pipe, right? So if we apply the energy balance now, and we are considering that the heat is coming in, so it means that for the steady state heat flow, energy in should be equal to energy out. So energy in, if we see that one is coming through this flow and one is coming from the surface of the pipe. So there are two modes of heat here. One is coming from the flow of this fluid, and one is coming from the by convection from the surface. So we can write yes.
सर ये जो कांस्टेंट हीट फ्लक्स की बाउंड्री कंडीशन है ये सरफेस से वाली है या जो फ्लूइड इन आ रहा है उसके लिए
But a constant heat flux, we are talking about the flux which is coming from the pipe surface to the fluid. We are not considering the heat which is coming from the x-axis. We are talking about the heat which is being transferred between the pipe surface and the fluid. Is it
ओके
clear?
सर
Okay.
जी सर
So now in this case, if we write it, so it would be equal to it would be equal to, we can write it, E dot in plus Q is equal to E dot out. So from here Q would be equal to E dot out minus E dot in. So here Q would be equal to M dot Cp Te minus Ti, which we usually call M dot Cp delta T, right? So that is something which we know from our thermodynamics knowledge as well. So now if we put the value of Qs into As here, we can write Qs into As. Qs into As would be equal to M dot Cp Te minus Ti. And then from here, if we want to know the value of Te, then that would be equal to Qs As divided by m dot Cp plus Ti. So we can write Ti plus m dot Cp Qs to As. Right? So this is the relation which we have got for this flow. Okay, one thing now. If we see here the second term on the right hand side, m dot for a given fluid flow, that would be a constant value. Cp is a fluid property that for any fluid that is constant. Qs, we have already said that that is the boundary condition, so constant heat flux. So that ought to be also a constant value. And then As, if we are talking about a particular length of the flow, so this whole thing is constant, right? So here AS, if we increase the pipe length, then AS would increase linearly. Okay, but for a given pipe, it would be a constant value. So if I draw here, let me draw. What should if this is the pipe now here. So now I say that here I am drawing the temperature distribution as function of x. X is the distance from the leading edge. X goes from here. So uh, there would be some portion which would have entrance region. So that is the here we have got LT, and then we would have fully developed flow here. Right. So now we have seen here. I am going to write the mean temperature. So or temperature. So at the inlet we have got Ti, and then what about TE? Because TE would be the slope of the line would be equal to m dot Cp upon Qs into As. So it means that it would linearly increase like this, right? So let me draw it again. Maybe not very steep slope. We can write it. Okay. Right. So this at this point this is T. Right. Okay, so now if I want to draw Ts on Ts is the surface temperature, how can I draw it? Is there any way I can draw it? First of all, please tell me that whether how can I write Qs here? Qs would be equal to from the Newton law of cooling, that would be equal to H into Ts minus Tm, right? So Ts would be equal to Ts is equal to Tm plus Qs upon H, right? So this is the relation for Ts. So one thing we can see that if Qs is positive, which is coming into the flow, then Ts would be more than Tm. So it means that if I draw Ts line here for the fully developed flow, not the best line I have drawn. Let me try again. Come on, just a minute. Let me. So this distance, that is constant, and that is equal to Qs upon H, because while that in the in fully developed region, H is constant. How do we know that? We know that from this curve, that in the fully developed region H is a constant, and secondly, because we are saying that the heat flux is also a constant value, so it means that this second term, that would be a constant value in the fully developed region. So it means that that would be parallel line. So this is a line of Ts, which is the surface temperature. Right. Now, what will happen when the flow would come in the entrance region? Because in the entrance region, if you look at the graph, H value is more. Can you see this? H value is decreasing. So it means that because now if I go back here, in this case, this H would be greater than QS, then it means that I would have a downward slope. It is a little bit difficult to draw a straight line on this tab. Apologies for this. So you can see now it has the distance between Ts and that fluid mean temperature is less. Why is this? Because H is more, and it means that the this difference would be, because if H is more, then this value would decrease. So that is something which is happening here. Okay, so that is why we have slope uh, when we come in the entrance region. So I hope that this point is clear to you all, right? So now, because we usually deal with the fully developed pipe flow, because usually the length of the pipe is far greater than the entrance region. So it means that we can safely consider it like a fully developed flow. So if we talk about steady laminar flow, if we want to know that what is the slope of this line along X, so it means that we need to determine for the fully developed flow, we need to determine dt upon ds, which would be equal to dTm upon dx, because this is the mean temperature at inlet and outlet. So I can say that this curve is for the mean temperature, right? So if I can know this slope, then it means that what does this slope tell us? That how rapid is heat transfer between the pipe surface and the fluid. So that is why we want to determine this slope. So for determining of for this slope, we can do the differential analysis. So uh, and then by doing the differential analysis, we can easily see that what is the value of this slope. So let me draw that differential element on a pipe, and then we can discuss that how we can determine uh, this slope. Okay. Objective of this is to determine this slope, so that because if the slope is more, it means that the fluid if inside the pipe is gaining more heat from the pipe surface, right? So that is why we want to know this slope in terms of mass flow rate and this QS value, which is the surface heat flux. So let me draw that again. And so now we are going to determine this slope of temperature rise by differential analysis. So let's consider we have got here a differential element. Okay, let me use some other marker. Uh, This is a differential element we are talking about. The thickness of this element is dx. Diameter of this pipe is d, and the temperature at the here I have got the temperature gained by this inside this differential element, that is dTm. So the temperature has been risen by dTm value. So it means that if temperature at the inlet is Ti, then at the outlet it would be equal to Ti plus dTm, because it is gaining heat. And the heat which is coming in, that is delta Q, that is equal to, it would be equal to uh, in it would be equal to Qs into ds. Okay. What is the value of ds? That would be equal to pi d into dx. Dx is the thickness of this, and then if I apply the energy balance, then I can write it m dot Cp Ti plus delta Q is equal to m dot Cp Ti plus dTm, right? So I can put in the values Ti plus, here I can write Qs into Ta, Qs into Qs into perimeter into dx, which is pi d is the perimeter, so I write it p into dx. And so here ds is equal to, I can write it perimeter into dx, where perimeter for a circular pipe is pi d, right? So perimeter into dx is equal to m dot Cp Ti plus m dot Cp dTm. So here, if I cancel out m dot, this would be cancelled out with this. From here, if I determine dTm by dx, that would be equal to dTm by dx. Let me see. So that value would be equal to, it would be equal to dTm by dx perimeter into peri perimeter into Qs divided by maybe Qs into P divided by m dot, right? So now it means that we know that how we can calculate the slope of this. So for this we can see that it would be dependent upon this. If the flux value is coming more, then it means that the temperature rise would be more. That is, physically we can say that if let me write it. If Qs is more, then delta T, which is T E minus Ti, that would be more. That is understandable, because if we are the flux value is more, then temperature rise of the fluid would be more. If the diameter of pipe, which is P, which is also directly proportional to diameter, if that is more, then delta T would be, again it would be more. And then if m dot is less, so it means that less fluid is coming in. If less fluid is coming in, temperature rise would be more. And then Cp value, which means that if the fluid can be heated quite easily, then it means then the temperature rise would again be more. Okay, so we can see this thing very easily. So it means that if the pipe flow, if the mass flow rate through pipe is increasing, then the heat heat transfer between the pipe surface and the fluid would be less, and that is the same thing we experiences in our geyser. So that, which means that if we have a high mass flow rate coming through pipe, so then it means that we need to provide more heating inside the geyser to have at, fluid coming at a fixed temperature. Okay, ji. So this is also equal to, because for the fluid developed region it is equal to this. So we can also write it dTs whole dx, and then we have found out this value. Right. So we can quickly see this through the slides and the things we have discussed. So I have already told you about 10 diameter thing, and then we discussed about this. That after 10 diameters, the flow can be safely taken as a fully developed 10 diameter of length of pipe, and then we discussed the two boundary condition. One was constant surface temperature, and then the constant heat flux. So for this case, for the we discussed that constant surface temperature boundary condition is there when we have got a phase change, and constant surface heat flux is realized when the tube is subjected to radiation or electric resistance heating. And when we talk about the constant heat flux boundary condition, we discussed that the mean temperature rises linearly, but the surface temperature decreases a little bit in the entrance region. Why that this slope is decreasing? Because the H value is more in the entrance region. And then we discussed that T can be written in terms of Ti when we apply the overall energy balance, right? And then here we discuss these relations, and then we discussed that how to calculate this slope dts divided by dx. So for that we applied the energy balance. If we apply that, that is equal to qsp upon m dot cp, and then we also know that in the fully developed region dtm upon dx is equal to dts upon dx, and then we can say that partial t by partial x is equal to dts by dx. That how can we do that? We can always use the condition for fully developed thermal region, and in that case, if we see 1 upon ts minus tm cannot be 0, so it means that this thing in the parenthesis would be equal to 0. So now we have said that it is a constant value because q dot s is also constant, parameter is constant, m dot cp. So that is what is, you can see it here in the figure, that in the fully developed region in a pipe which is subjected to constant surface heat flux, temperature gradient is independent of x, which means that it would have a constant value temperature gradient, right? So it means that the profile would remain the same. Okay, now if we want to write it q dot s m dot cp a little bit, if we want to put in the values of because we have got this, so let me pen there, and now we can write that p is equal to pi d, and then uh, m dot, that is equal to rho av. We know that rho av means, so what is area of a cross sectional area of pipe rho AC? So pi by 4 d square into Vm. So if we put it here, so then dTm upon dx would be equal to Qs into pi d divided by rho into pi by 4 d square into Vm. Now if we kind of do the uh, simple, uh, we simplify it by, and then we would have diameter would go with this, so we having 4 us 4 us divided by rho d n. So now we can write it in terms of diameter and mean velocity rather than m dot. So this is the relation, we can write it here. So uh, yeah, okay, so pi d into yes, so that is fine because r is if we put d by 2, so it would be 4 qs upon rho vm cp into d. So that is equally good. So now we have seen that how we can calculate the slope. Okay, so now if you remember that in tube bank case, no, this was a discussion about the constant surface temperature, the constant heat flux. So now we are going to discuss the uh, sorry. Now we are going to discuss the second boundary condition, which is constant temperature, constant surface temperature. Let's suppose we have got this pipe. Now here I have got Ts is equal to 100 degrees, which is uh, which is which is 100 degrees centigrade, and then here I have Ti is equal to 10. Now if I show it here in the graph, so along the length I have got the same temperature, which is Ts is equal to 100 degree centigrade, and at the inlet I have got Ti is equal to 10 degree centigrade. Now at the when the fluid comes into contact with this pipe surface at the inlet, because we have got the maximum temperature difference, and we know that Q is equal to H into Ts minus Tm. Tm here would be Ti. So it means that this temperature difference, that is maximum at the beginning, and on top of that H value is also more in the entrance region. So that is why we would have certain temperature rise here. So it would be exponential kind of rise, and then because as we move along, because the temperature difference, this Ts minus Tm would decrease along the length. So it means that the heat transfer would also be a little bit gradual. So it is kind of this, uh, exactly this. So it cannot approach this. So it is kind of the asymptotic line. So, if you remember that in flow over tube banks, we also taken surface temperature of all the tubes one equal value. So that is why we also experienced we are we had also experienced this kind of curve for the temperature rise in flow over tube bank. So that is why there we use Q is equal to HAS into delta T logarithmic, and then we discussed that delta T logarithmic was equal to delta Te minus delta Ti divided by log of delta Te divided by delta Ti, and then here delta Te is equal to Ts minus T, and then here delta Ti similarly Ts minus T. So that is which we have discussed up to now. And then we also discussed that if we want to determine PE from this, then in that case we discussed that that is PS into PS minus TI into exponent minus HES on m dot C. Now, from where this thing came, this exponent, this thing is called NTU. We would come to that what is number of transfer units in a bit. So first of all, we need to know that from where these relations were derived. Because for the case of tube bank, we just took it as it is, and uh, we have said there that we would derive it for the when we come into internal flow discussion. So let me uh, write that equation again. If we go back for the differential analysis, sorry, where we get the differential analysis. Here, here we written that QS into PDX is equal to m dot Cp dTm. So let me do this differential analysis, and then we would come QS into PDX is equal to m dot Cp dTm. So let me write it again, this equation. Right. So now, what is for the constant surface temperature boundary condition? Because dTm can be written like minus T into Ts minus Tm. Can we write it? Is there a problem with this?
No, sir.
Because you can see that it would be equal to minus dTs plus dTm. No, because there is constant surface temperature, so this first term would be always equal to 0 for this boundary condition. So we can easily see that this would be true for this case, right? So now, uh, if we see that what is Q here? Okay, what is Q? Q is the heat flux, right? So heat flux, if we remember from our chapter number 1, convective heat flux, so we remember from there that Q value is equal to H into Ts minus Tm. Okay, because here there is no T infinity, so we are writing Tm. So if we write these two values in this equation, so it would be equal to m dot Cp. Instead of dTm, we would write minus d into Ts minus Tm, right? So mathematically it is right. Then we can also write H into P into Ts minus Tm into dS. So from here, if we separate the variables, so what we do that we write Ts minus Tm here, dt d of this divided by Ts minus Tm, we write it here, and then we write it Hp upon m dot Cp, and this minus would come here, and we write it dx. Right. So we already know that H is a constant value in a fully developed pipe flow. P is also constant value. M dot is constant for a given flow rate. Cp is constant. So if we do the integration from from x is equal to 0 to total length of the pipe, so it means that here it would be from Ti to Te. So if we do the integration, then we know that for the quantity on the this left hand side, the integral would be equal to log of Ts minus Tm Te on Ti, and then here it would be Hp into m dot Cp into length of the pipe, H into Pl. So now if we do the simplification, it would be equal to Ts minus Te minus log of Ts minus Ti is equal to minus H into perimeter into the length of the pipe is the surface area of the pipe. So HAS upon m dot Cp. So now we can write it log of Ts minus Te divided by Ts minus Ti minus HAS on m dot Cp, and then from here, if we want to calculate t, we need to take the antilog on both sides, which is the exponential function Ts minus Te divided by Ts minus Ti would be equal to exponent minus Has on dot Cp, and then if we calculate sorry, so we can write it here. So from here we calculate T, that would be equal to Ts minus Ts minus T I exponent minus HAS upon m dot C. So that is the same relation which we use in chapter number 7 when we talked about the flow over tube bank. And now the second bit is that how to see that formula for the logarithmic temperature difference, right? So now we take this equation which is here. Natural log of Ts minus T divided by Ts minus Ti minus Hs upon m dot Cp. So now if we talk about this, let me pen it a little bit. Now, if we write it here, from here, if we want to calculate the value of m dot Cp, then that would be equal to, sorry, I can use black, and m dot Cp would be equal to minus Has upon log of uh, log of Ts minus Tb Ts okay. So here it would be Ts minus Ti. Now we know the relation for total heat transfer, that is Q is equal to m dot Cp Te minus Ti. If that is the total heat gained by the fluid, so that would be equal to this. So instead of m dot Cp, we can write this. Uh, so we put this thing here, this thing here. So we are putting instead of m dot Cp, which is here, we are putting this whole quantity. So if we do that, it would be HAS into into it would be equal to HAS into Ti minus Te divided by natural log of Te no, not Te, Ts minus Te divided by Ts minus Ti. Right. So now, even then, we haven't got. Now, if we do a little bit of manipulation, that add Ts, add and subtract Ts on the denominator. Okay. So if we do that, so that would be equal to Q is equal to HAS into, then first we add Ts minus Te minus, then we do that, we subtract it. When we subtract it, we can write it like this, and then Ti divided by log of Ts minus. Right. So now if we see that this term, this total, that is equal to delta T natural log. So we can write it Q is equal to HAS delta T log. So now you can see that how we have derived these two, this relation. So now one thing which is left here, that is because I told you that this quantity, that is, we call it NTU, which is m dot uh, uh, which is HAS upon m dot Cp. So what is the physical significance of number of transfer units? Let me show you by one that tells you about the potential of heat transfer. Okay? So how does it mean that what is the potential of heat transfer? So we discussed these things up to now. And here if you see HAS upon m dot Cp, that is number of transfer units. So uh, this number of transfer units tell us about the potential of heat transfer within a pipe. So, if the number of transfer units are, if its value is quite less, if it is less than 1, it means that if we increase the pipe length, it would give us substantial increase in heat transfer. So, let me write it here. Because if you see that NTU, there is HAS upon m dot Cp. So AS here, that is P into. So if NTU value is less than less than 1, then we say great potential of heat transfer by increasing its value. How can we increase the value of NTU? Either we can increase the length of the pipe. So it means that if we draw that curve again here, that T curve, so it means that we are somewhere. Uh, we discussed that it goes like this. So when NTU value is less, it means that we are somewhere here in this region. Okay? So if we increase the pipe length, then it would give us more increase. But if it is kind of somewhere length is quite uh, big, then it means then it would be in this area. Then even if we increase the length, so if NTU is more than 5, then there is no advantage of increasing the pipe length. Pipe length. While that when NTQ would be equal to 5, then it would be in somewhere here. We are talking about somewhere here. It means that even if we increase the length, because the temperature difference between the surface temperature and the fluid temperature is very less, so the heat transfer would be increased very slightly. So what is the practical problem? Practical, if I give you the number that what I am talking about, if we consider a flow through a pipe in which the surface temperature is 100 and we have been given the inlet temperature is 20. Now you can see a table of NTU at the bottom. So if the NTU value is 0.01, then the TE value would be 20.8. But if we increase the NTU value to 0.05, you can see that the temperature has increased by 3 degrees, right? So it means that it is still less than 100. So it means that we can increase the NTU value. Now NTU value, how can it increase? Either by increasing the length of the pipe or by decreasing the mass flow rate through that. So then if we increase it to 1, you can suddenly see that when NTQ is increased from 0.01 to 1, its value jumped by 50 degrees. Okay? So, but when it becomes equal to 5, then it means that the exit temperature of the fluid, it is 99.5. So even if we double it, double the pipe length, then it increased only by zero point 0.5. So it means that if NTU value is around 5 or this less than 5 and more than 1, we have got the maximum heat transfer. We have managed to get the maximum heat transfer. So there is no point of increasing the NTU value beyond 5. So the feasible value is between 3 to maybe 3 to 5. 3 to 4 would be even 3 to 4 is a very good feasible value for NTU. Whenever we are designing any heat exchanger, we need to make sure that the NTU value for that pipe is in the range of 3 to 4, because at 1 there is still uh, 30 degree which the fluid can gain, but if we increase it to maybe 4, then maybe 95% heat would be transferred. So that is the concept of NTU. So now let's have a break of 5 minutes, and then we can do one numerical problem for this, and then we have discussed this derivation, uh, right? So for this case, we can have a numerical problem after the break. So let's have a break of 5 minutes, and then at 4 p.m.
Okay, sir.
Okay, uh, so we were discussing about general thermal analysis before the break. So let's do one numerical problem to see that how we can apply that knowledge in a physical problem. So water whose CP value is given enters 2.5 centimeter internal diameter in copper tube of a heat. I think this is extra of a heat exchanger at 15 degrees centigrade. So I would kind of remove it at 15 degrees centigrade at a rate of 0.3 kg per second. So and it is heated by steam condensing outside at 120 degrees centigrade if the average heat transfer coefficient is 800 watt per meter square Kelvin. So now the heat transfer coefficient is given. Determine the length of the tube required in order to heat the water to 115 degrees centigrade. Now it means that TE value is given, but we need to determine the length of the tube which is required to heat this pipe. So if you see that we haven't discussed the Nusselt number or the H determination at the moment, but we would come to that maybe after this numerical. So so I hope that you are able to hear my voice. Is that correct? Can anyone confirm?
Yes.
Okay, thank you. Thank you. So now we have been given this data. So first of all, what we can do that we can determine the total heat transfer rate through this that it would be equal to m dot Cp Te minus Ti. So m dot is 0.3, then CP value is 4187. So please remember that you have to put CP value in joule per kg Kelvin, not in kilojoule. Whenever you because if you do that in kilojoule, then the value would be in kilowatt. So if we do that, so it comes out to be 125.6 kilowatt because we have divided it by 1000 to get it into kilowatt here. So now we know this value, and then this heat transfer would be equal to the heat transfer by convection through the pipe surface. So because for this case, the boundary condition is constant surface boundary condition. So it means that we need to apply Q is equal to HAS delta T logarithmic. So in AS we need to know the value of length. So that length would come here. So if I go on to the whiteboard, so for this problem, this Q value we determine it from m dot CPTE minus TI, and then this is equal to H into pi dl, which is surface area into delta T logarithm. Okay, H value is given, so diameter is known to us, and delta T logarithmic that would be equal to delta TE minus delta TI divided by log of delta TE upon delta TI. So what is delta TE in this case? That would be equal to TS minus T to TE, which would be equal to TS here is 20 minus 115, so it would be 5. Then delta TI in this case would be equal to it would be equal to 120 minus, sorry, what have I done? So if we see here, then delta Ti would be 120 minus 15, that would be equal to, that would be 105 degree centigrade. And then once we know these value, we can determine delta T logarithmic, and then m dot that is given, and then Cp is also given, so we can determine the length which which we need to determine here. So if I show you the calculation, that is straightforward. There is no problem. 5 to 105 delta T logarithmic. That is okay. Q dot we have already calculated, and then here it would be H value is given. That is zero point 0.8, and then delta T logarithmic 32.85, and then from here we can calculate AS, and then AS is equal to pi dl. So diameter is known to us, which is uh, 25 millimeters. So in this case, length comes out to be 61 meters. So it means that we need 61 meter pipe length in order to raise the temperature from 15 to 115 degrees centigrade. And you can obviously see that we cannot have that 61 meter length by a straight pipe. So that's why in heat exchangers they are usually there are turns in that network of pipes. There are kind of turns by which we obtain this the length of the pipe in a confined volume, right? So that is something we can also see those turn in the pipe uh, outside our fridge or inside the coils of that air conditioner. So that is AS. Now, but even in this problem, if you see that H value is given to us, right? And for a given mass flow rate. But usually in the practical problems, that if we know the m dot, then we know the mean velocity. And then for each mean velocity, we need to determine this H value, which is given here. So that is something which we did by the Nusselt number correlation for the external flow. So that is the same thing which we are going to do for this. So first of all, we would go through the derivation for the Nusselt number, because if you remember this, if I take you back a little bit, that if we talk about the laminar flow, for the laminar fully developed flow, if you see that H value becomes constant in the fully developed region, so we can derive we can expect a constant value of Nusselt number for fully developed laminar flow, right? So for the constant surface boundary condition and the constant surface heat flux boundary condition. So we are going to derive those constant value of Nusselt number for one of the boundary condition, and then the similar can be applied for the second boundary condition. So, but before doing that, we need to know the mean velocity relation. So first of all, we would do that. But for the turbulent flow, we need to rely on the empirical correlation or the ANSYS software, which we are learning at the moment. So the deadline is the 31st Jan. So first of all, we discuss the laminar flow in tubes. Okay, have you discussed this thing in your FM2 course?
जी
Anyone?
सर
Okay, and do you know the relation between mean velocity and the velocity profile? This relation, have you came across this? B of r minus r square upon u in terms of this pressure gradient.
सर ये नहीं अभी तक शायद किया
Okay,
कर
you
लिया मेरे ख्याल है।
जी जयाद
मेरे ख्याल सर ये हमने कर लिया टर्बुलेंट के अंदर।
कर लिया
ये, ये वाला रिलेशन आपने पढ़ा है
यार
जी सर,
लेकिन
टर्बुलेंट के अंदर पड़ा है।
ये आतिफ ने कहा है कि जी what did Atif he wants to have more enlightenment about
Yes,
this
sir.
topic. जी, चल,
सर बता
कोई
दें
नहीं
थोड़ा
बेटा,
सा और सर।
वो मैंने लिखा हुआ है, ये देखे ना बोल्ड में, derivation section 8-5. So you can go through the simple derivation to get to this profile because that is not very difficult. So you can handle that. I'm 100% confident about your abilities. So because here the main crux is what the heat transfer, so we would go through that. So that derivation is done. So from here, if we want to calculate the mean velocity, we know that we derived one formula here in the beginning of this chapter for the mean velocity. That was, if we go back here, Vm is equal to 2 upon r square into Vr of f into rdr. So we are going to use this, that we have seen that, and we put that value in this relation. So if we do that, so 2 upon r square, that is there, 0 to r, Vr, dr. So instead of Vr, we just put this value here, r square upon 4 mu dp by dx. So this bit r square, because r is the this diameter of the pipe, internal diameter of the pipe. So because that is a constant value, this would come out dp by dx. That for a given flow that is given, so that is also constant value. It would come out of integration, and we are left with 1 minus r square upon capital R square into rdr. So uh, if we do that simple integration and put the limits, then I'm sure that we would be able to get minus r square upon 8 mu into dp by dx. So do you want me to do this simple integration, or you can manage it at your own? I think you are more than capable of doing that.
जी
करवा दें।
सर कर लेंगे सर।
Okay, ji. Just for once, we can agree to the request of Atif. So maybe we can spend 2 minutes on this. So that would make Atif a little happy. So we can do that. So if we kind of, okay, it means that here we can paste it. Sorry. Okay. So we have got this. So now if we do try to do the simplification here, so it would be minus 2 upon r square into r square upon 4 mu into dp by dx. It would be out of integration, and then inside the integration we would have 0 r into, we would have r into dr minus r cube on r square into r into dr, 0 to r. So here here we see that r square would be cancelled out this, 2 this. So minus, it would be minus 1 upon 2 mu dp by dx. Now inside the integration we would have r square divided by 2 minus r raised by 4 divided by r square, and then limits we know 0 to r, 0 to r, right. So minus 1 upon 2 mu into dp by d should be dp by dx, like dp by dx. Here it would be r square. I think you haven't spotted a mistake. It should be for r square here, so it should be r square by 2 minus, if we put the limit, r4 divided by 4 r, so it means minus 1.2 mu dp by dt. Here we would have 2 r square minus r square. Okay, so I hope that this derivation is clear. So then it would be minus 1 upon 8 mu dp by dx into r square. So that is the value of Vf. So let's see that is it the same value or not. I think we have been able to minus r square upon 8 mu. So let's see, minus r square upon 8 mu dp by dx. So it is the same thing. So it means that we can do it. So now if we see the first relation, right, kind of snap it. Just a minute. Let me do it. Copy and then if you paste it here somewhere. Now if you see that VM and VR are quite now you can see that they are quite similar. How they are similar? Because we have got if we write VR here again, if we want to introduce 8 mu, then we need to kind of multiply it with, and then here it would be 2, and then dp by dx, and then 1 minus r square of r. Now this bit is equal to Vm, which we have already. If you see that this bit is the same thing which is written here, so what we can do that we can replace it and we can say that V of R is equal to 2Vm 1 minus R square upon R square, and then if we put at R is equal to 0, which is the center line velocity, then center line velocity becomes equal to 2Vm. So it means that at the center line of the pipe we would have maximum value, which would be 2 times into mean velocity, and then at the pipe surface we would have zero velocity when we put R is equal to capital R. So that is which we have learned from our FM2 course, I hope. So that derivation I have done here, V of R is equal to 2Bm into 1 minus R square upon R. And then because dP by dx is the gradient, so we can also write it in terms of delta P, which is because what is dP by dx? If I kind of write it here, dP by dx is basically pressure at the final value minus pressure at the initial value divided by the length of the pipe. And if we talk about pressure drop, then that is P1 minus P2. So then we can write dP by dx is equal to minus delta P divided by total length of the pipe. So if we replace that, then we can if we replace dP by dx here with delta P by L minus delta P by L, and then minus would be cancelled out with this minus, and then from here delta P would be equal to 8 mu into length of the pipe into Vm divided by R square. If we want to write R square in terms of diameter, it would be basically d square by 4, and then that 4 would take it 32 mu L Vm. So it means that for a given, okay, so then we have also know that delta P is equal to FL upon D mu. It shouldn't be mu here. It should be rho Vm square upon 2. Have you came across this formula where F is the
जी सर, ये
starting?
की है.
So here, if you see that there is some mistake. In the Sengel's book, it has written mu Vm square upon 2, but it is never mu here. It is rho Vm square upon 2. Okay? If you remember from your FM2 course, so it means that people who print the books, they can also make mistakes. So please be vigilant of that because it shouldn't be mu here. So because I have copied it from the Sengel's book, so that's why it is mu here, but it shouldn't be mu. It should be rho here, if you remember from your FM2 course. So please correct it at your end. So I just deliberately keep it like this because just to show that we can always make some mistakes. So please be vigilant of that. And then if we compare these two relations, then we can easily see that F becomes equal to 64 upon Reynolds number. Have you came across this formula as well? 64 upon Reynolds number.
जी सर.
Okay, so it means that friction factor, which is more important in fluid mechanics, that is inversely proportional to the Reynolds number in case of laminar fully developed pipe flow. So we are talking about fully developed laminar pipe flow. So then the pumping power required, we know that this is volume flow rate into delta P, and we can always write it volume flow rate in V mean into, just a minute. So V mean into cross sectional area, and then if we do the integrate, if we do the manipulation, mathematical manipulation, we can write V dot in terms of pi d to power 4 into delta P into 128 mu L. So it means that if for a given diameter, if we require horsepower, so if we increase the diameter keeping the same volume flow rate, then we would have 16 times less because we are decreasing. If we are increasing the delta P, so you can easily see that when it would go in, on this side, it would be coming in the denominator. So for a for a uh, for a narrow pipe, if we want to have a fixed flow rate, then maybe we would need 16 times more horsepower for the same volume flow rate if we use the wider pipe. Okay, double diameter pipe, then we would require less horsepower. Okay, if the volume flow rate is the same for the both pipes. So I think that you can readily see this, that for the narrow pipe, because the friction would be more, the resistance to the flow would be more, so the horsepower requirement would be 16 times more for double diameter, for half diameter pipe. So now, because there was a numerical problem, so I just put it here, but that is not very relevant for the heat transfer. But because in the synthesis book that is here, so we can do it. Water at 14 degree Fahrenheit, rho value is given, mu value is given. It is flowing through a pipe 0.12-inch diameter, 30 feet long, steadily at an average velocity of 3 feet per second. Determine the pressure drop and the pumping power. Very simple. First of all, we calculate the Reynolds number. If Reynolds number is less than 2300, it means that we can calculate a friction factor, which is 64 upon Reynolds number. So friction factors come out to be 64 divided by 1803, which comes out to be 0.0355. Now delta B is equal to FLD into rho Vm square upon 2. Now, in the previous slide, it was mu, so that was wrong. That was incorrect. It should be rho here. So, F value we have just calculated. Length of the pipe is 30 feet. Diameter is 0.12 divided by, because diameter is in inches, we have to put it in feet because length is in the feet. So, either we convert length into inches or convert diameter into feet. So we need to do it in feet because the velocity is also given in feet. So then we can do that change of pound mass per feet square into pound per square inch by dividing it by 32.174. So if we do that, we get the value 6.46, 930 pound force divided by feet squared. So if we want to do it in psi, we need to again divide it by 144, then we get 6.46. Then the volume flow rate, Vm into AC. Vm, we have been given the value, mean velocity 3 feet per second, and then AC, we can cross sectional area. Then from here, volume flow rate is calculated, and then we can calculate the pumping power. Now, in the next class, we would be discussing that how we can derive the Nusselt number correlation for the constant surface heat flux. Okay, so we wouldn't be doing all the derivation, but we would see the key steps there, and then we would see that how that can be done. So we would do that in tomorrow's class, and that's a reminder that we would have your quiz number 4 from chapter number 6 and 7 in tomorrow's class. So please be prepared for that. So it would